Have you ever wondered what gives a lemon that sharp, puckering taste? Or why soap feels so slippery on your hands? Well, the answer is all around us, in two of the most important characters in all of chemistry, acids and bases. We're going to build a toolkit to really understand them, not with a bunch of scary formulas, but by seeing how they literally shape everything, from the food we eat to our own chances of survival. So here's our game plan. First, we're going to get to the bottom of what acids and bases even are. Then we'll uncover water's secret and surprisingly active role in their whole story. After that, we'll grab a tool to measure them, see how they can be strong or weak, watch them react in real time, and finally discover how they pull off the incredible job of keeping systems, like, our own bodies, in perfect balance.
All right, let's grab the first and most fundamental tool in our kit. And we're going to start with a question you've definitely experienced yourself.
Right, the easy answer is acids and bases. But what is really going on? It all comes down to this tiny, invisible little dance that's happening at a molecular level. And once you see the moves, everything else just clicks into place. Okay, this right here is the key moment. See, when an acid hits water, like on the left, it immediately lets go of hydrogen ions. And on the right, when a base hits water, it releases hydroxide ions. That simple act, releasing these specific charged particles, is where all their power comes from. So let's zoom in on the acid. Now, a hydrogen atom is just one proton and one electron. So a hydrogen ion, that's H+, has lost its electron. It's literally just a bare proton. So an acid is simply a proton donor. Its entire purpose in life is to give that proton away. And what about the base? Well, it's the acid's perfect dance partner. It's a proton acceptor. It's chemically designed to catch the protons that acids are tossing out. This constant give and take, this donation and acceptance, that is the proton dance. It's the core secret to all acid-base chemistry. So where does this proton dance usually take place? Well, on the world's most common stage, of course, water. But here's the twist. Water isn't just a passive backdrop. It's actually an active player in the dance itself. Check this out. Water molecules are constantly doing the proton dance with each other. One water molecule acts as an acid and gives a proton to another water molecule, which acts as a base. It's called autoionization, and it means that even the purest water you can find always has a tiny, steady amount of acid and base ions floating around. And this is where it gets really cool. That relationship between the acid and base ions in water is totally locked in. It's like a chemical seesaw. If you add more acid and the H+ side goes down, the OH- side has to go up to keep things balanced. This constant, predictable relationship is what makes water such an incredibly stable and reliable place for chemistry to happen. Okay, so we've got a handle on what acids and bases are, but how do we talk about how acidic something is? For that, we need our next tool, a simple ruler for measuring acidity. And here was the problem chemists faced. The actual concentration of hydrogen ions is usually this tiny, absurdly long decimal number. It's just clunky. Imagine trying to write that in your notes or shout it across the lab all day. There had to be a better way. And there was. In 1909, a chemist named Soren Sorensen came up with this incredibly elegant solution, the pH scale. It's basically a clever math trick that takes that awful decimal number and just focuses on how many zeros are after the decimal point. It turns a total mess into a clean, simple scale that usually just runs from 0 to 14. And suddenly, you see this scale everywhere. A low pH, like battery acid or even your own stomach acid, means there's a high concentration of those H+ ions, so it's very acidic. A high pH, like a household cleaner, means a low concentration of H+ ions, very basic. And sitting right there in the middle, at a perfect pH of 7, is pure neutral water. So now we have a scale to measure things, but there's a bit more nuance here. Turns out, not all acids are created equal. The next tool in our kit helps us tell the difference between something that's truly strong and something that's, well, a little weak. It really all comes down to commitment. Think of a strong acid like a fire hose. The second it hits water, it unleashes all of its protons, all at once, in a huge blast. But a weak acid? It's more like a garden sprinkler. It only lets go of a tiny fraction of its protons, while most of them just stay attached. It's the same dance, just a very, very different level of intensity. And we can actually put a number on that sprinkler effect.
It's called the acid dissociation constant, or Ka. You can just think of it as a willingness to donate score. An acid with a bigger Ka score is more willing to give up its protons, making it a stronger weak acid. But a teeny tiny Ka score? That means the acid is super reluctant and holds on to its protons really tightly. It's a whole spectrum of strength. Okay, time to put all these new tools to work. How do chemists actually use this stuff? Well, one of the classic techniques is called a titration, and it lets us literally watch the story of an acid-base reaction unfold from beginning to end. So the process is actually pretty straightforward. You take your acid, but you don't know exactly how concentrated it is. Then, drop by careful drop, you add a base that you do know the concentration of, and all along the way, you measure the pH. When you plot that data on a graph, you get a picture that tells a story. This graph is the whole story of the reaction. See how at first the pH climbs really slowly? That's the acid fighting back. But then, bam, you hit the climax, this huge, dramatic, vertical jump. That's called the equivalence point. It's the exact moment when the very last molecule of acid gets neutralized by the base. After that one drop, the fight's over, the base takes over, and the pH levels off again. That crazy sharp jump in the pH shows you just how sensitive these systems can be. So, how does anything in the real world, like, say, our own bodies, avoid these wild swings? Well, that brings us to our last and maybe most important tool, the buffer. And this is where it all becomes, quite literally, a matter of life and death. Your blood has to stay in this incredibly tight pH range, right around 7.4. If it shifts too much in either direction, your body's systems just start to shut down. The only reason we're all alive is because our blood has this amazing chemical team, the bicarbonate buffer system, working around the clock to keep that pH perfectly stable. So how on earth does it work? Well, a buffer is basically a solution that has a team up. It's got both a weak acid and its partner base living together. So if some rogue, strong acid gets into the system, the base part of the buffer jumps in and neutralizes it. And if a strong base shows up, the acid part of the buffer takes care of that. It acts like a chemical shock absorber, soaking up any excess acid or base to keep the pH right where it needs to be. So you see, this chemical toolkit isn't just for a lab. It's the very system that keeps our blood stable enough for us to live and our oceans stable enough for life to thrive. Understanding this chemistry means understanding one of the most fundamental balancing acts on our entire planet. And it leaves us with a pretty critical question. What happens when we push these natural buffers past their breaking point?